Determine the horizontal and vertical components of reaction at the pin A and the reaction of the rocker B on the beam. Okay, let's start with some assumptions. Let's first start with it's going to be a massless, widthless beam. It's also going to be a rigid beam, so that means it's not going to deform with any of the loads applied to it. Just a couple assumptions to make this calculation a little easier. Okay, let's start with the find variable. All I can do is just to stay organized. We're looking for the horizontal components at A and the vertical component as well, and the normal reaction at B. So label that NB. Okay, let's start with a free body diagram. Even though this is a massless and widthless beam, it's still important to draw it with some width, just for like ease of understanding. Let's label the beam. Got point A right here, point B right here. And if a problem gives you a labeling system, I recommend using those just so you don't get confused with a different system. 6 meters from there and 2 meters here. Going for left to right on the beam, we have a pin reaction at A. Like I said earlier, it'll resist both horizontal and vertical forces. It will not resist moments, however. The beam would be free to rotate around A if there's no other forces acting on it. So, all right, get a force AY and a force AX acting on the beam here. Okay, and going left to right, we have a point load 4 kilonewtons right here, acting 6 meters from point A, and we have the reaction at B right here as well. So the reaction B here is a rocker, which will give a force reaction that is perpendicular to the surface right here. And the surface, the angle here, I should say, is given in terms of the surface right here and not the reaction force. So we have to find that angle in terms of the reaction force. Okay. So if we put green here as the reaction surface right here, we know it's perpendicular to reaction force, so we can put a 90-degree angle there. And we know in terms of the horizontal right here, this will be 30 degrees. Given from this angle right here, 30 degrees right here. And that creates a nice triangle, which would let us know that this angle right here is 60 degrees. And that'll be an angle in terms of the reaction force vector and the horizontal. So I just clean that up right there. We know the angle is 60 degrees and it's in terms of our reaction force. Okay, let's move on to our equations of equilibrium. Okay, since we have 3 unknowns, we'll be needing 3 equations. Even though this is a 2D problem, there's 3 axes that we need to account for equilibrium, for total mechanical equilibrium. So let's sum the forces around A first. People usually sum the forces in X first, but I think summing the moments around A will make this problem a little easier. We're going to sum the moments around A because it'll cancel out the moment that caused by AX and AY because there's no moment arm, so it'll just be left with 2 moments, so I think it'll be a little easier. So we have the force 4 kilonewtons is the first force going left from right. That'll be creating a moment about A. It'll be 4 kilonewtons, and that'll be acting 6 meters away from point A, and that'll have a negative sign on it because that'll be spinning the beam clockwise about A. So just using the regular right-hand rule sign convention. And then we'll be going to the other force that'll be acting on the beam. That'll be creating a moment with a reaction NB. It'll only be the horizontal reaction here that will be creating, no, I should say the vertical reaction here that will be creating a moment, because a horizontal reaction doesn't have a moment arm, so there'll be no moment created. So to find that vertical component, we'll take the sine of 60 of the reaction at B right here. Okay, that'll be positive because it'll be spinning the beam counterclockwise about A. And that'll be acting 8 meters from point A. Set that equals 0. We have one unknown, the normal reaction at B, so I'll make it relatively easy to solve for. Plug that into your calculator. You should find NB should be equal to 3.46 kilonewtons. And that's our first find variable. So I'll write it up here to make sure we're solving for what the problem's asking for. Okay, then we'll move on to sum of forces in the X. So going from left to right, we know AX is acting towards the right, so it'll be a positive sign for that. And then the only other force we have acting the horizontal will be the horizontal reaction at B, which will be negative because it's going towards the left. Know that it is 3.46, that reaction at B, 3.46 kilonewtons, and we're looking for the horizontal reaction, so we'll be taking the cosine of 60 of that to find the horizontal reaction. Set that equal to 0 because the beam is at rest in the x-axis, in terms of the x-axis. So one unknown, pretty easy to solve for. Plug into your calculator. Should find AX is equal to 1.73 kilonewtons. Okay, and that's going to be your second find variable. So write it up here, 0.73 kilonewtons. Okay, and now let's sum the forces in Y to find our last unknown. Going left from right, we have the reaction at A. AY will be positive because it's going in the upward direction. We have that point load, 4 kilonewtons, acting in the negative direction. So we will give it a negative sign in our equation, 4 kilonewtons. And then we have the reaction at B, which is 3.46 kilonewtons. And to find that vertical component, we'll be taking the sine of 60. And positive because it's acting upward. One unknown in this equation, AY, pretty easy to solve for. You should find that AY is equal to 1 kilonewton. And that'll be your last find variable. So put up here, we answered everything the question was asking for. And if you notice that all these reactions are positive right here, that means in our free body diagram, we defined all the forces in the correct direction. If we got a negative for any of these reactions, this means that we assumed the force was going the wrong direction and that the force is actually acting in the opposite direction.